invitation, it wasn't completely clear to me what the audience was going to be. So I will be, I don't know how well known, how much background people have on Hyperkahler manifolds in general. I'm going to assume not very much and try and explain things, but stop me if everybody knows what I'm saying. And then I will try to say this. In other words, I've got two versions of this talk, one for specialist Hyperkahler audiences, one for everybody else. You'll get to hear everybody else.
But unfortunately, Misha Lubitsky, he is in Brazil now. Our main specialist.
Well, yeah, but you don't need to, the thing is that there's some sort of gap between being a Hyperkahler specialist and being Misha, so so general public and then the Hyperkahler people and then there's Misha. So, okay, so let me at least start by giving you, okay, so I'm trying to write down the definition, I didn't think it's already started. Right, so I'm interested in compact complex manifolds. Maybe algebraic, but not necessarily. I would like to know which ones are. So here's a definition of a class of compact complex manifolds, and I'll try to explain why we're interested in them. So a compact complex, this is the definition, compact complex manifold X is called, well, it's either called irreducible polymorphic symplectic manifold, or actually, I think I want to say irreducible holomorphic symplectic manifold. Let me say that first. If, well, I want it to be a compact Kahler manifold, I want it to be simply connected. And then the main thing is that I want there to be a two-form, which distinguished two-form, which gives me all of H20, and so H0 of omega 2x is generated by sigma, where sigma is an everywhere non-degenerate. Okay, so that's the definition of irreducible. Irreducible means this bit, means that this is the statement that this is one-dimensional. Holomorphic symplectic is the existence of this non-degenerate, everywhere non-degenerate two forms, symplectic form. Right, so that's a class of manifolds. I've just written it down for no reason at all. Okay, so in particular, though, of course, because of this, these are K-trivial manifolds. Okay, and the other thing is because I've got non-degenerate symplectic forms around, the complex dimension here is even. So, in particular. Trivial even complex dimension. Okay, so this is so I've given the definition of irreducible holomorphic symplectic because that's what I'm going to work with really. What I used in the title is Hyperkahler. So you should think, of course, of having a P1 of complex structures, you can vary. And it is a non-trivial theorem that those are equivalent. I won't write the precise statement. The reason it's non-trivial is that in one direction one's using Yau's theorem. So it's not something that you just look at and go, oh, of course. But on the other hand, if you accept Yau's theorem, it's trivial now. Well, it's not completely trivial now, but it's fairly trivial now. But there's a hard, non-obvious theorem in the their unit. Okay, so there's also a third, so let me just say equivalently, X is Hyperkahler, i.e. There are complex structures. Complex structures. I, J, K stuff. And the other equivalent thing, which perhaps isn't as well known as maybe it should be, is that these are exactly, so this is another equivalent condition, the Riemannian manifolds. With SPR polynomials, one of the classes of special polynomial manifolds. Right. So, so these are interesting. Even if you're only interested in Riemannian geometry, you're going to want to understand these manifolds. The reason, I think, from my point of view, in terms of as an algebraic geometer, I'm interested in complex algebraic varieties. A little bit more of a stretch, I'm interested in compact complex manifolds. If you want to understand compact complex manifolds, then your, say, complex algebraic varieties, projective algebraic varieties, then you're going to have to understand something like Farner manifolds. You're going to have to understand varieties of general type or despair and say that that's too big and complicated, you can't. And you're going to have to understand things which are k-trivial. Kappa equals 0, could either dimension 0. Anything in between, you come with natural vibrations and you can work with them. Some kind of inductive procedure going on, which again is very non-trivial, but at least you've got a handle on them. So we want to understand k-trivial manifolds, and then the reason I'm particularly interested in this one from that point of view is that, in fact, so I think that this is from Moloch. Any k-trivial let's say, not worrying too much about the precise conditions, is A cross X cross Y. So A is here as an abelian variety. Y is a genuine Calabi-Yau. And X here is one of these. And by is, I mean is up to, say, some finite covers. But again, I just want to know which things have I really got to understand. So we're going to. So we know that we've got to understand k-trivial varieties. We're not going to get any help from anything else. Those we've got to understand. And then when we look deeper into that, we find that we've got to understand each of these three classes separately, and then we've got some sort of grip on anything else. Okay. So this is an important class. That makes this an important sort of fundamental class of compact complex manifolds that we really like to understand, and we don't really expect them to be much like anything else. They're just a sort of different kind of objects. In particular, they're not really going to behave very much like these ones. There's no particular reason they will. Okay, so do you want me to write down the review form for you? I think what I'll do next is just tell you which ones there are, which you probably already know, but let me write the list. Okay, so your first question might be whether there are any of these at all. Well, there are K3 surfaces, so there are some, and then actually for a while it was believed that there were not anymore, but there are. And then, so the examples. So the first one is you look at Hilb n of S with S, a K3 surface, and deformations of those. So I didn't say whether my K3 surface was algebraic, and I didn't really care very much, but by saying Hilb scheme rather than Dewey space, I suppose I am saying it's algebraic, but then I don't mind because I'm going to take deformation anyway. Okay. So for the moment, I'm not actually particularly concerned about whether these things are algebraic or not. Sometimes they will be, sometimes not. So this is a very well-known one to mention in the last talk. And then there's the generalized cumulus. So Km n plus 1 A. So what you do is you take an abelian surface A. So A is an abelian surface. And so you have a map from the, if I look at the at Hilb n plus 1 of A, that comes with a map to A, which is just addition on the, away from the diagonals, where this is just a symmetric product, and then extends over the diagonals by half or something, and you look at the fibre over 0. And these ones here are the Km, well, I think I want to call that n plus 1. It's, the dimension here is 2n, by the way. Okay? And then there are things called OG6 and OG10. And these are particular moduli spaces of sheaves, but very special ones on, and then I rather wish I'd put those the other way around, actually. Doesn't matter. So that's very particular moduli spaces of sheaves on K3 or abelian surfaces. And again, I should always say plus deformations.
These are resolutions of singularities.
They are resolutions of singularities of those, yes. And in fact, that's why they have to be very particular moduli spaces, because if you write down a moduli space of sheaves on a K3 surface, it comes more or less for free under really weak conditions. It comes more or less for free with symplectic structure, but it also has singularities. Generally speaking, you can't do resolution of singularities in symplectic geometry the way you can in complex geometry. And so what you need to do, you have a form like this on the smooth part, and what you need to do is to be able to resolve the singularities in such a way that the form extends. Essentially, you want something like a small resolution. So the OG here, this is Kieran O'Grady. Those numbers are the numbers of dimensions dimension 6 and dimension 10. And these both date from around from the late 1990s, something like that.
99.
So
99.
90, one of them's 97, one of them is 99, something like that.
And they don't have analogs on
Sorry?
They don't have analogs on Hilbert.
When you say they don't have analogs in Hilbert, I mean, this is a moduli space. This is a, I mean, if you like, here's a moduli space of sheaves on a K3 surface, and here's another moduli space of sheaves on a K3 surface. And I'm saying those ones, you can resolve the singularities. Here there aren't any. And you get away with it. And then you look at other moduli spaces of sheaves, and it doesn't work.
Moduli space is smooth, right? It's two-dimensional cube.
So, I mean, the thing that I do want to point out is that I've always got these and deformations. I mean, these are just some points in the moduli spaces. So the other thing to say is, if I look at this one, for example, I mean, there's an obvious deformation I can do, which is to deform S. But if you do the calculation, it's rather easy. Oh, the deformations are unobstructed. This is a general, fairly easy fact about Hyperkahler manifolds. The deformations are always unobstructed. But this actually has one more deformation parameter, which doesn't come from deforming the surface. So in other words, if you look in the deformation space, most of them are not actually Hilbert schemes of K3 surfaces or direct spaces of K3 surfaces. Okay. And so the thing that I want to draw your attention to really is to say, look, I mean, we've got these 4 examples. And we've had these 4 examples for 20 years now, and we have made no further progress. So,
No progress with new examples, you mean?
yeah. Well, neither with examples nor with. So that's fine. So I'm now going to make a responsible statement, and then qualify it until it becomes a little bit more responsible. Right. So, suspicion. Okay. I mean, I suspect. There aren't any more. Well, dimension 4, so of course that's not telling us anything about these two. Okay, so this is a sort of irresponsible statement of mine. Nobody else is responsible for it. I believe that Manfred Lehn has been. I haven't actually heard him do this, so I don't know whether this is really the case. But somebody told me that Manfred Lehn had been saying that he thought that there were lots more, but I think what he has in mind is in things of rather high dimension. First of all, I don't actually know that he said that. Somebody told me that he'd been heard to say that, so bad enough that I'm making irresponsible statements of my own. I certainly shouldn't make irresponsible statements on behalf of other people.
No, but nevertheless, we'll have rather weak condition of the numbers.
Yeah, but I mean, there are lots of, so the Bogomolov form, what we know about the Bogomolov form doesn't, about what the Betty numbers could be, yes, I mean, that's right. I mean, we don't, well, okay, so perhaps that's my point. I mean, so.
It would be nice, really.
But B2 is not more than 23.
Yes, but that's still, yeah, so, yes, but even then, first of all, that's still many more numbers than we actually can realise, and the other is even if we knew the right Betty numbers, there could still in principle be many different deformation types that just happen to have the right Betty numbers with different
No, singularities are much more. So maybe the smoothness is just there is no condition.
Well, I think that might be right, yes. I think that might be right. Okay, so anyway, my reason for this suspicion is slightly more than just the passage of time, but it's not really sort of completely mathematically based, because we do have different ways of constructing Hyperkahler manifolds, and quite a lot of constructions. So what methods? So what methods do we know of constructing Hyperkahler manifolds? Well, I can think of three. So one of them is moduli of sheaves, which is the way that I've described these here. We pretty much know that, at least as things stand, that's pretty much exhausted. We don't absolutely know that, because I haven't told you sheaves on what. So far, we've done this by looking at sheaves on K3 surfaces and abelian surfaces. So, why not something bigger? Well, what bigger things would do? Well, probably some of those, but then that's not going to give you anything new.
Cubic fourfold.
So,
Cubic fourfold.
cubic fourfold, yeah, I mean, one could, but so there are other things one could try, but certainly the moduli spaces of sheaves that we've seriously tried looking at, moduli spaces of sheaves on K3 surfaces and so on, we pretty much know that that won't work. In other words, that these cases of O'Grady's are, it's not quite a theorem, I think there's still a little bit of wriggle room in that, but we'll pretty much know that those are the only ones where you will actually be able to find. I'm not quite sure what the status is. I mean, it's certainly there was some sort of little exception about it's something to do with stability, but yes, you may be right.
If I remember correctly, I mean, I should know because my name is on the paper, although I didn't. No, it's Manfred, not Christoph, but I think the theorem is that if you have a moduli space of sheaves on a K3, I think all.
Okay, yes. I mean, that's certainly my understanding. Realistically, all of them,
Yeah, but it's not like objects in K3 category, which is not
so you want to look at, rather than moduli sheaves, you want to look at the derived category, think of a sheaf as something concentrated in degree 1.
On the surface itself, some other formation, the category can deform a little bit.
So you want to
The famous practical resolution of singularity is a pretty strong condition. And what happens
Yeah, exactly.
is that as soon as you're out of these cases, the dimensions of single strata are so large
that you've got no chance of getting the kind of small resolution. Exactly. Okay. So those we think are exhausted. Okay, at least for now. I mean, one can imagine that we might find some new object and then we can do that to the new object, but until we find, we would need new input. And then I think you're right, we would then have to be extremely lucky. The second thing, so I mean obviously people do this very well, never mind, I'll carry it on regardless. So the second thing is projected geometry constructions. So the cases that one knows are e.g. Final varieties, only final varieties in the sense of the minus k alpha. I mean final varieties of parametric spaces of lines. Yeah. Four. Always do that, I don't know why. That point I always write through it. So final variety. Etc. because there are quite a lot of others. So miscellaneous projected constructions that people have found. And the thing that's striking about that, and this is I think what really leads me to this suspicion, is that, I mean, you do these, and you're not, so you start with a construction like this, and there's no other geometry in sight. You do this, you end up back in this case all the time. You don't find I mean, it's not because there's a K3 surface hidden in the picture to start with, because what you get is one of these deformations. So there's no actual K3 surface around, but, you know, typically, if you like. So that's how it's depicted. So, yes, yes. I mean, so, you know, there are a lot of these, there are quite a few of these constructions, and yet somehow we keep landing in the same place again. And so one sort of suspicion is that that's happening because there isn't anywhere else to land. Okay, so there are some arguments against that. Let me say what they are. One of them is we seem to land in this case, not that one. I don't know, and I would be interested if anybody does know, of any explicit example of a deformation of a generalized Kummer variety. I mean, the only way I know to get the deformation of a generalized Kummer variety is to take a generalized Kummer variety and deform it.
You want the global, or I say, sorry, the formal one.
So, and
Okay, there's this trick. You take K3 and the take it's not going to do deformation. So it doesn't exist.
yeah,
It only exists at the final order.
yeah.
Up to final order, it gives you a deformation of the Hilbert scheme as a model. You do the same with a billion.
Okay, but again, you still have to start with one of these things and deform it. And whereas this kind of construction starts with something that on the face of it has nothing to do with K3 surfaces, and it just hands with one of these guys. It never seems to hand one of these guys. I mean, so I think there's a... so, you know, if I didn't know about these already, then I would be arguing that they don't exist. So, maybe that's not. The other reason, actually, to be a little bit suspicious of this argument is that these constructions, because they're projective geometry constructions, typically they involve taking some Riemannians or something like that, they always give you rational families, just because of the way they're set up. Now, we know, because of the sort of things that are in class and I proved, that the moduli spaces, the polarized moduli spaces, we're doing all this in projective geometry, so we're going to get polarized varieties. And these polarized moduli spaces, they are mostly a general type. So they tend not to contain much in the way of rational subvarieties, it's certainly not unirational themselves. So if one had another class where the moduli spaces were actually all of them of, you know, very hyperbolic general typings, no, they're just, in other words, one could imagine having classes of manifolds, but they just do not come in rational families, whatever you do. In which case, you're not going to find it by this kind of global projective geometry methods. Local deformations are the only thing going. So you need to find this, we need to find this one. So those are sort of reasons. That's what I say. I'm now arguing with myself. I'm trying to explain why maybe this suspicion is ill-founded. But nevertheless, this kind of, I find this rather striking that we keep turning up new methods, new geometric methods of constructing Hyperkahler manifolds, and yet we're not finding any new Hyperkahler manifolds. Okay. So the third method that I can imagine, and I'm sure that there are people with more powerful imagination. Sorry?
Projective geometry is hard to do even for some old manifolds to do it by big methods. Prove that you have smooth variety.
Oh, no, but my point is people succeed in doing this. I mean, okay, so Claire Fontaine succeeds in doing this.
Radius from cubic fourfold, but
very few examples.
Yeah, no, there are very few examples, but well, no, not so few now. After five, 6, that kind of. But yeah,
not 20 to a 30.
No. But yes, on the other hand, I think we have reasons to expect that. We kind of know why this is happening. We know that there aren't big rational families. We know there aren't lots and lots and lots of big rational families. Nevertheless, I find it striking that we keep finding these ones. Okay, so the third thing is the third construction that I can think of is to construct the degenerations first, and then try to smooth. And so I think, I don't think that anybody, this is not the world's least obvious idea, but I'm not really aware of any very serious attempt to do this. And there are reasons why not, it's quite hard. Nevertheless, I kind of like this because it's the only thing that I think of so far which gives me any chance of, we're a long way away, but suppose I'm right, suppose there actually aren't any more. How on earth are you going to try and prove that? So I'm essentially trying to classify all Hyperkahler manifolds in some fixed dimension form. I don't know how to go about this at all, but what I do know is that, so I'm being sort of deliberately vague here, because I don't actually know anything. So Aragon said in his talk that he asked a question, and then he said, I'm now going to tell you the answer, because otherwise it would be a bad talk. So I'm going to give you a bad talk. I'm asking the question, are there any more of these Hyperkahler manifolds? Can one construct degenerate manifolds first? I don't know. But I think it's interesting to try. And I think it may be worth trying, at least to get some kind of information. So so let me talk a little bit about degenerations of Hyperkahler manifolds. So again, this will be very well known to some people, not so much about degenerations of Hyperkahler manifolds, but if we think about the only case we really do know, in the case of K3 surfaces. So that's the only kind of Hyperkahler manifold we really understand. So, well, we know what the degenerations look like. So essentially, there's type 1. This is Kulikov, and it's sort of 76, 77, something like that. And also,
100 years ago.
So, yeah, he did it a long time ago. We've known this for a long. So this was so the Kulikov, and then also there's also Pinkham and perhaps Tyler, some parts and bits and things. And so type 1 is essentially that means essentially still K3 surface. So there's a K3, the thing's degenerated, but one of the components is still a K3 surface, and then maybe it's sprouted some other stuff. You've done something stupid like take a smooth family and just pick one of the fibers and blow up some points, something idiotic like that. And then type 2. There's an elliptic curve in the picture somewhere. And so these are one-dimensional. These come from one-dimensional families. So there's an elliptic curve in the picture somewhere, and the J invariant, or whatever other modular invariant it's got, of the elliptic curve parameterizes these. So a typical one of those looks something like you have a string of surfaces. You've got an elliptic curve here. It's the same one. So you've got, so these are elliptical surfaces or something like that. And then there's some extra structure. So these are one-dimensional, and then type 3. These are what I might call toric. So what I mean by that is that they are so they're zero-dimensional. There's no real moduli left in the picture anymore. So a typical fibre here looks like a bunch of toric surfaces meeting transversely along toric strata. And then one knows something about what those do. You look at the dual complex, and that should be an S2. So, I mean, if you think of this, this is obviously analogous to those elliptic fibers. Okay, So the point is that this kind of trichotomy is still there for Hyperkahler manifolds. So the thing I have to say, I don't, how much time have I got? 20. Yeah, okay, right. Let me say a little bit then about where this comes from. So I mean, so these are, it's kind of not really telling me anything new at all, because you've still got the same problem, just hidden inside. But these come from, if I do everything polarized moduli, which is the way I tend to prefer to being an algebraic geometer, these come from strata in the boundary of the moduli space. So the moduli space of polarized Hyperkahler manifolds is given by up to some problems caused by Torelli not really working the way you would have thought at first. The moduli spaces really look like some symmetric domain modulo some group, and gamma is some subgroup of some O2n. Okay. So what's happening is this O2n, the Hyperkahler manifold has a quadratic form on H2, not on the middle cosmology, it's got an active form, it's got a quadratic form on H2, which is essentially given. So the first time I gave a talk about this, this form is called, it has the names of Bovil, Bogomolov, and Fujiki on it in various combinations. So the first time I gave a talk about this, about 10, 12 years ago, not about this, but about Hyperkahler manifolds, Bovil was in the audience. So it had to be Bovil form, but then the next time I gave the same talk, Fedor was in the audience. So I have to adjust that. I've never met Fujiki. Sorry?
He discovered this form in the paper where he also proved that Hyperkahler manifolds look this.
Well, yeah, I think I alluded to that. I think that's before you came in, but yes. He didn't prove they don't exist. There were K3 surfaces. There were K3 surfaces, but no ones.
Yeah.
But it's nearly true. So.
It's nearly true. Yes. Okay. So he's nearly right. That's what I'm saying. Okay. So so this comes from. H2. So this has a quadratic form on it, and the so Shevarditsky has a Torelli theorem for Hyperkahler manifolds, which doesn't say quite what you would think it would say. It was about the third or fourth attempt to and it was a while before we got the right statement. Without worrying too much about those technicalities, essentially there's a moduli space which is given by a symmetric space associated with this quadratic form, modulo some group of.
This is called algebraic, I mean, for polarized.
These are the polarized ones, yes. Well, explaining why that's harmless. So because of the 2n here, there are isotropic planes and isotropic lines and nothing else. So the Veda-Borel compactification has dimension 1 boundary and dimension 0 boundary, and dimension 0 boundary is big. So the dimension 1 boundary are modular curves, and the dimension 0 boundary is the cusps of those modular curves meeting in some configuration that one can work out if one felt like it. And so that's the modular curves are the things that are parameterizing these elliptic curves. And then this is what happens when you get to the dimension 0 boundary, which corresponds to its either. I never remember which way around it is because it's different in the symplectic case. But one of them is either the dimension 0 boundary is the planes, I think. But no.
Yes.
Do we know that universal family extends to the Borel?
I'm sorry?
Do we know that the communication response to some actual family?
Well, no, we don't even know that for K3 surfaces. I mean, it's a very difficult question whether there's really whether there's some sort of universal family over some suitable compactification.
Like opening your point at the bottom.
Sorry?
even like locally near a point.
Well, that's really what I'm wanting to say. I mean, that's precisely the issue. So this is the thing that I can do a little bit towards. So globally, I think that's a really hard question. So even for K3 surfaces on degree 2, we don't really have a good answer to that question globally. Locally, I think there is something that we can say. So one thing to point out is something Valerie mentioned. I'm thinking about polarized varieties implicitly. I'm thinking about algebraic ones. This is actually fairly harmless because the algebraic ones are dense in the. So I think this is Verbitsky again, or maybe Karen knows that. I'm not sure who's actually responsible for the base. But if you look at the deformation space of any Hyperkahler manifold, there's the algebraic one's dense in that. So I'm not really giving anything away.
That thing I think is kind of classic because it's on core structure, so it's kind of.
Well, I think to get back to the actual manifolds, you probably need the Torelli theorem.
Could be, yeah, well, whatever. In any case, it's
I think it's basically a corollary of the Torelli theorem. But yes. So I'm not really giving anything away by looking at only algebraic.
And that's one thing you can do because if you look at non-algebraic, the action of discrete group is horrible.
Oh, absolutely. No, I mean, it's the only thing I can do. But fortunately, I'm allowed to do it.
We still have complex structure, but not closed door.
They actually become.
No, this
actually is nice.
No. This statement. Yes, I mean, if I go up to 3 something, then you get some completely. Well, I mean, it's very non-household. I mean, but Hyperkahler uses that. So he walks around that space by using the twister lines, by using the Hyperkahler structure as a way of connecting things together. But certainly for what I want to do now, I definitely don't want to have to think about non-algebraic things. Okay, so I think that the question then is, do we have any chance of understanding? So the one that I think that there's some chance of the one I'd like to elaborate on is these, because. These ones should be given by some toric things, which will be given by combinatorial data, meeting according to some prescribed, satisfying some prescribed combinatorial conditions, which reflect the fact that there's that 2 form which I've rubbed off nearby. So in other words, I want to be able to write down central fibers in the degeneration of the disk, which are they're toric, basically toric things. I can smooth them, and I'm guaranteed on the nearby fibers. I'm guaranteed 2 form with the right thing. So there should be some kind of residue on the central fiber that tells me that there used to be the 2 form nearby. And I would like to be able to capture that information. Okay, so that's kind of the sort of thing that one would like to be able to do eventually, and we're a very long way from that at the moment, but that's kind of distant aim. So ideally, I would like to be able to say a type 3 degeneration of a Hyperkahler manifold is, the central fiber is, or can be reduced to after some standard moves. Some toric varieties meeting according to the following rules, following kinds of conditions, some kind of extra data, maybe a lot of or something like that, and then there's a condition for smoothability, and then you would then you've at least got a combinatorial problem, and there's some kind of boundedness about it. We might actually be able to get a grip on. That's the kind of general thinking. Of course, what I really mean is I'm going to push this problem off, would like to push this problem off into combinatorics, where it's not my problem anymore. I'm going to reduce the problem I can't solve to another problem that somebody else can't solve. That's progress. I'm a long way from being able to do that. Let me say what I can do. So what we would like. So I'm not the first person to have kind of false. So I've got, okay, I've got a few minutes. Right. So
there are three types of degenerations.
there are three types of degenerations.
And
Type,
domain is called type 4.
sorry?
And domain is called type 4.
The domain is a type 4 domain, yes. We can't really hold this. Okay, so let me just say the little bit that I can do. So the little bit that I can do is that in some cases, so far very limited cases, I can do the sort of thing that we've been asked about, we want to do locally. So in other words, what we like, let me write down a definition. Let me write down, so this definition is due to Nagai, who attempted to do this some while ago. So this definition. Nagai, 2008. So a good degeneration, so this is the definition of good degeneration. And he's rather tentative about it, since he isn't sure whether it's the right thing. Of an irreducible symplectic manifold. Irreducible symplectic manifolds is a semi-stable family such that so this is over a disk, so I'm just doing this, I think the global question of whether their family is really hard, very interesting, but it's really hard. So this is just over a disk, or even a spectral disk over a DVR if you're an algebraic geometer, such that there exists a relative log 2 form, so it's allowed to pick up poles along log poles along the central fibre. So sigma, it's in h0 of x, and then it's the relative relative two potentially these poles at where
Zero.
sorry?
X.
X0 is the fibre of this O0. So this is a semi-stable family, so the central fibre is a simple normal crossings device. So this is smooth. I'll come back to that. But this is smooth, and the central fibre is a simple normal crossings divisor. So Mumford's semi-stable reduction theorem tells me that I can, if you give me a family, I can reduce it to this form if you allow me to take to make a finite base change, which I'm certainly happy to do. So this is a simple normal crossings divisor. So this here makes sense, okay, because it's a simple normal crossings divisor. It's given by vanishing products of the local coordinates. And so if I just say, well, I'm allowed dx over x poles, nothing else, that's all right. Okay. And then such that, if you look at the top, I think I've already called that sigma pi, if you remind myself pi is still there. If I look at that, this should be, so this is, I look at the top exterior power of it, and this should be never vanished. So this is the sort of. So this is essentially saying that you've got a family over a disk, and you've got some global object upstairs, which accounts for the two forms on the fibres, but it's global. It extends in a reasonably sensible way over the central fibre as well.
M is dimensional.
Sorry, n is the dimension.
Half dimension of
Yeah, the dimension is the dimension is the yes, it's the 5 dimension n, 5 dimension 2n. Yes. Okay, so you can write down this definition. The question is, do these exist? They ever exist? Write down all the definitions I like. Okay, so what Nagai proves so what he does is he takes a degenerating family of K3 surfaces, he takes a type 2 degeneration of K3 surfaces, and he just looks at the relative hill2 of that. Now that's not semi-stable.
And then you modify it.
Then you modify it, and you check that you can do one. But you say then you modify it, it's not completely trivial to modify it, because I do want this, the other thing I want to semi-stable families, I don't want it to be projective. If I do small modifications, those aren't necessarily projective. So I can't just do, it's not enough in other words to be able to modify them to deal with each singularity separately. That's not, so projectivity is the issue.
It was projective and Calabiero together.
You might be able, well, except I'm doing this on the central fibre where things are possibly quite bad. I mean, it's, yes, I mean, if you do type 1, then yes, but so Nagai showed us that if this is a type 2 degeneration, I'll say a little more about that. How much time have I got? Yeah. Of K3s, then the relative hill, I'll just call it hill, I think he only does it for hill 2, of S over delta can be modified to give a good degeneration. So this is a very special case. And then he says that one can maybe do this for type 3, but it looks as if it's going to be more difficult. The reason he says it's going to be more difficult is that what he does. So let me explain. So, okay, so let me tell you what I can do. I mean, so one, I should at least I should be able to do at least one thing. Okay, I can do at least one thing. So the Zhu Zhang and I. We can do this type 3. So this is really, this is pretty weak. I mean, this is not major progress. I'm not claiming it is.
Or second position.
For hill 2, yes. I mean, well, I tried to do it for hill 3 as well, and I think I can, but it's a horrible mess. But if I've got a minute again, I'll explain why I've kind of stopped trying to do that. For the moment, anyway. Okay, so let me explain very quickly what Nagai does and why he thought he wouldn't be able to do it for type 3 and why I think he can. Well, why I can. So what Nagai does is he looks at his type 2 degeneration. So the central fibre looks like this. We've got S1 and then some Sn here. Okay, and then that gives him a picture of the center. That's okay. So this is bad notation because S1 up to Sn are the components of S0. But S0 is the central fibre of the. And now he looks at what the Hilbert scheme looks like. So of course you have components Yij, which you get by taking one of your points in the ith component and one in the jth component, and you see how they fit together. And they fit together like this. You get a core of a chessboard. And then at these points, something weird is happening. And what he does, but this is very bad for singular. What he does is he blows up these components. So the ones, he sort of goes up even one because this sign convention is opposite from mine. And the point about doing that is that each of these corners is adjacent to exactly one of the things he's blown up. So what happens is he replaces that corner with something like this. Yeah. And of course that choice isn't the only choice he could make. If he blew up this one instead, then he'd be doing some kind of flop at this point. But you should expect that. You shouldn't expect these things to be unique at all, because you should be able to do flops. In fact, so Kulikov's paper was really one of the first cases of minimal model theory in action. I mean, before minimal model theory was even there. But essentially what you've got is you've got a threefold, and you are trying to modify the singularities in such a way as to take account of canonical devices. Okay, so he does this, and then he says after he's done that, because he's making, the point is because these are blow-ups all the time, that's automatically projective. So he doesn't have to worry. And all he's doing at these points is when he blows this up, at most points this is a Cartier divisor, so it doesn't make any difference. But here, at this singular point, it's only a Weil divisor. When you blow up, something happens, and what happens is you pull a curve out of that singularity and resolve it. So you do these small resolutions, and but you don't do them by hand in each corner. You do these global blow-ups, and you get the right thing. So we get a similar picture. But my observation is simply, you see, what he worries about is trying to get the right picture so that he hits each corner exactly once. My observation is that I don't care. I get a similar picture. It's more complicated. I won't try to draw it. But I get a similar picture where I'm simply going to go around all these components and blow up every single one in some order. Which resolution I get will depend on the order I do it in. After a while, I've actually got a resolution, but I don't know. And I keep going on blowing things up, but they're Cartier devices. It doesn't matter if I blow them up, it's an isomorphism. What I have to check is that if I do blow up everything, I resolve the singularities, but that this actually works. And then I try to do it for type 3, for hill 3, and it should work, but you have to blow up some things more than once, so it's rather messy. But, let me say one other thing, which is that I actually think that this is, so when I did this, I thought, yeah, okay, Nagai was actually being modest. This is the right condition. The reason I think it might not be is that I think insisting on this being smooth is too much. So there's a paper recently by Janusz Kolar, Radulaza, Julia Saka, and Claire Voisin. And so, anything signed by any of those people is likely to be interesting. With all four of them, it's probably doing something fairly drastic. What they do actually is they look at type 1 degenerations, mostly for a different reason. But they essentially, the condition that they say, and I think that this is correct, that the condition you should have here should not be as strong as smooth. It should be, I think, divisorial log terminal is one of these many different conditions one has in birational geometry. That seems to be maybe the right thing. And in that case, maybe already this is overdoing it. So I haven't gone back to look at that yet. So that's why I stopped trying to push this any further. Also because it's such small progress. But at least one can do something. Sometimes we can understand what some of these degenerate fibers look like. We have some examples. Maybe we can begin to understand what's going on. I'll stop.
Okay, are there willing?
If you're doing do it the other way around, that you start with something with log structure, the smooth like how much and how.
Yeah.
The other space you get is it smooth or not?
So this space.
Yeah.
Well, I think it depends what, well, it would depend on what the log structure is. I mean, what I want, of course,
So
is
it's kind of both.
I think it could be both, yes. I don't think there's, I don't think, so actually one of the, I didn't mention this, there's also a PhD thesis of one of Manfred Leeds' students, which among other things, he tries to do more or less that actually. He's kind of inconclusive, I mean, it's a PhD thesis, he never really finished.
What's the name of the student?
Hanke. I think he left mathematics, so so it's all slightly incomplete. And he also wants to do something a bit like this, but he wants to do it a bit differently. And he actually didn't check things correctly. And what he gets is he gets something where his total space is not smooth. He says it is, but it's not. But maybe it's divisorial log terminal, so perhaps I don't care.
Yeah, I mean, this kind of divisorial log put it on the level line on key things. They don't
Sorry?
really- those kind of MMP things,
Mhm.
they don't really play together nicely with subjective formulas that we and you probably really want to think about log structure.
I think that may well be right, actually, yes. But somehow, yeah, you mean in order to see the symplectic form rather than just top exterior power. Yeah. I think that's probably right, but on the other hand, you do need to get the canonical part right first. So
Yeah, that's for sure.
so that possibly determines roughly where to go. Anyway, so it's all very speculative. I've got lots more speculation. But that's speculation you don't have to stop. You see it all. You look over, you can stop.
Okay, other willing to continue discussions? No?
Coffee breaks.
Okay, let's have the coffee break until 5 p.m.